We are in chapter 6, where we discuss transformation of stresses and strains, failure theories, and thin-walled pressure vessels. This is the first session in chapter 6. Here we discuss transformation of stresses in two dimensions. Here we have a glimpse of the sessions covered in the first 4 chapters. In the last chapter, we discussed shear. We are now in chapter 6, where we start off by discussing transformation of stresses. In this session, we primarily looked at developing formulas on transformation of stress. Here we look at transformation of stresses. Consider a point in a body subjected to loads. Let the stresses acting at an element at that point along a particular alignment be known. Then it was first discussed in chapter 1 that if that element is rotated, then the stresses will vary. If the element is rotated, then at certain angles, the normal stress will become maximum and minimum. Also, at a certain angle, the shear stress will become maximum and minimum. Later on, we mentioned about the variation of stress due to rotation in chapter 2 and chapter 4. This was done in relation to normal stress theory and shear stress theory. For normal stress theory and shear stress theory, we have to find the absolute maximum normal stress and absolute maximum shear stress in a body. So the maximum normal stress and the maximum shear stress at points in a body are required. Till now, the discussion has been mainly physical. In this session, we'll provide the theoretical background. After establishing the theoretical background, we'll also go through a geometrical procedure. However, let us first reiterate the physical understanding that we have discussed before. In chapter 1, we mentioned about a bar subjected to tensile loads as shown here. A section was taken perpendicular to the axis of the bar. If we consider the equilibrium of this portion, then we can find out the stresses acting on an element as shown. A side of the element is aligned with the section. The element is subjected to a normal stress sigma x and sigma y is 0. There is no shear stress acting on the element. In chapter 1, we then took inclined sections passing through the same point. If we consider the equilibrium of the left to an inclined portion of the beam, then we can find the stresses on an element whose side is aligned with the inclined section. We considered inclined sections at several angles and found that the normal stresses acting on these elements were in between sigma x here and sigma y, which is 0. So for a given rotation, this element gives the maximum normal stress and the minimum normal stress. If we consider this alignment as alpha is equal to 0, then at alpha is equal to minus 45, and alpha is equal to plus 45, we found that the maximum anti-clockwise and clockwise shear stress acts. Now consider another case. This is a beam subjected to a load P with reactions at A and B. Let us consider a section 1-1. Then it is subjected to a moment RAX and a shear force RA. Let this element be in between the neutral axis and the bottom layer. Due to moment, there's normal stresses acting on this element, and due to shear, there are shear stresses also acting on this element. If we keep on rotating this element, then at a certain angle, we'll find that the maximum and minimum normal stresses will act, and there will be no shear stresses acting on the element. So the case is same as here, except that the maximum normal and minimum normal stress acts when the element is at an angle. So if alpha is 0 here, alpha has some magnitude in this case. However, also here, if we consider alpha minus 45 and alpha plus 45, then we'll get the position where the maximum anti-clockwise shear stress and clockwise shear stress acts. So the behavior discussed here is general for any element in a loaded beam, except that the angle here can change. So alpha can be different from 0. All this will be established theoretically in this session. In reality, an element in this beam is a three-dimensional element as shown here. However, there are no stresses in the z direction. So we mostly represent this element in 2 dimensions. We can analyze this case using 2 dimension for most problems. However, there are few problems where we'll revert back to the 3-dimensional case because the 2-dimensional case cannot be used. The rotation of this element is shown in this figure. So here theta is kept on increasing till we attain a full turn. However, one would notice that with the arrangement of stresses given in this element, if we rotate the element by 180 degrees, the arrangement of stresses is the same. A 180-degree rotation will give us the stress variation. We obtain algebraic equations of transformation of stresses. Consider an element as shown here with the stresses acting on it known. Let us rotate the element by an angle theta in the counterclockwise direction. So this is the rotated element. The stresses acting on it has changed. So this normal stress is sigma x dash. The shear stress is tau x dash y dash. And this normal stress is sigma y dash. So now we'll give algebraic expressions of these new stresses. As earlier mentioned, relationship between stresses are obtained by first converting them So we convert the stresses into forces and then use equilibrium equations. In chapter 1, we showed that the magnitude of tau xy and tau yx are equal. This relationship was obtained by first converting stresses into forces. The rotation theta of the horizontal can be also considered vertically. BC is aligned with the right face of this element. To find expressions, we'll consider equilibrium of the triangle ABC. The separated triangle with the stresses acting on it are shown here. The triangle is considered to be of unit thickness. The normal stress acting on the face BC is sigma x dash, and the shear stress is tau x dash y dash. We'll first determine an expression for sigma x dash. The relative dimensions of the sides of the triangle are given here. So AB is BC cos theta and AC is BC sin theta. We'll solve forces along the direction of sigma x dash. So we'll use the equation summation f x dash is equal to 0. We get sigma x dash into BC minus sigma x into AB to cos theta minus sigma y into AC into sin theta. We write tau yx as tau xy. So we get tau xy into AC into cos theta, which is negative, minus tau xy into AB into sin theta is equal to 0. Now in this equation, we replace AB and AC as BC cos theta and BC sin theta. So we get this relation. BC here is common to all the terms, so we can take BC out. Then we get the relation sigma x dash is equal to sigma x cos square theta plus sigma y sin square theta plus 2 tau xy cos theta sin theta. Now 2 cos theta sin theta is sin 2 theta, and cos square theta and sin square theta can be written in terms of cos 2 theta. So here, instead of writing sigma x dash in terms of trigonometric functions of theta, we have written sigma x dash in terms of trigonometric functions of 2 theta. Arranging, we get this equation, that is sigma x dash is sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cos 2 theta plus tau xy sin 2 theta. Here we'll resolve the forces along the y dash axis to obtain tau x dash y dash. So we use the equation summation f y dash is equal to 0. So we get tau x dash y dash into BC plus sigma x into AB into sin theta minus sigma y into AC into cos theta plus tau yx, which we have written as tau xy, into AC into sin theta minus tau xy into AB into cos theta is equal to 0. We then substitute AB is BC cos theta and AC is BC sin theta. In this expression, BC is common and we can take BC out. So tau x dash y dash is given by this expression. Here sin squared theta minus cos squared theta is cos 2 theta, and we can write cos theta and into sin theta in terms of sin 2 theta. So substituting these values, we get tau x dash y dash as minus sigma x minus sigma y divided by 2 whole bracket into sin 2 theta plus tau xy cos 2 theta. Earlier we obtained this relationship for sigma x dash. We can obtain sigma y dash by using this expression and replacing theta by 90 plus theta. So sigma y dash is given by this expression. Now cos 90 plus theta is equal to minus sin theta, and sin 90 plus theta is equal to cos theta. Substituting these values, we get this expression for sigma y dash. Placing sin squared theta and cos squared theta in terms of cos 2 theta, we get this expression. So sigma y dash is equal to sigma x plus sigma y divided by 2 minus bracket sigma x minus sigma y divided by 2 cos 2 theta minus tau xy sin 2 theta. Pairing sigma y dash with sigma x dash, these terms are the same, except that there is a negative sign when we are finding sigma y dash in front of the second term and the third term. Till now, we have determined the equations of transformation of stress. So this is the equation of transformation of sigma x. We'll now find out the angles at which the normal stress becomes maximum and minimum. We'll also find the magnitude of such maximum and minimum normal stress. Or we can say that we'll find out the direction and magnitude of the principal stresses. To find out the direction of the maximum and minimum normal stress, we differentiate it with theta and equate it to 0. In this equation, these two terms are not functions of theta. So we differentiate these two terms and take this term to the other side. We then get this equation. The angle corresponding to the principal stresses is denoted as theta dash. And from this equation, we get tan 2 theta dash is equal to 2 tau xy divided by sigma x minus sigma y. Now from trigonometry, we know tan 2 theta dash is equal to tan 180 plus 2 theta dash. Hence, we have two values of theta dash that will satisfy this equation. We designate them as theta dash 1 and theta dash 2. These two angles will be 90 degrees apart, with one giving the maximum normal stress and the other the minimum normal stress. From this equation, we can form this triangle. It helps us to find out the other trigonometric functions. So here we give sine 2 theta 1 dash and cos 2 theta 1 dash. Since sine 180 plus alpha is equal to minus sine alpha and cos 180 plus alpha is equal to minus cos alpha, we get sine 2 theta dash 2 by adding a negative sign in front of this term, and we get cos 2 theta dash 2 by adding a negative sign in front of this term. So we have two sets of sine and cos theta values, which will give us the same tan value. Now substituting theta dash 1 in this equation for theta, we get this equation with the positive signs. Now substituting theta dash 2 for theta in this equation, we get this equation with the negative signs. So this equation accounts for both theta dash 1 and theta dash 2. We substitute the values of cos 2 theta dash 1 and sine 2 theta dash 1 from here. We now carry out some algebraic manipulation. We multiply sigma x minus sigma y, these two values, and also tau xy, these two cases. Next, instead of two terms, we sum up the terms to get one term. We then end up with this expression for sigma maximum and sigma minimum. With the positive value, we get sigma maximum, and with the negative value, we'll get sigma minimum. Sigma maximum corresponds to theta dash 1 and sigma minimum corresponds to theta dash 2. Now consider the fact that this term and this term are both positive. Then this term for the maximum normal stress will have a larger value. Consider one value is positive and the other negative. Then this term of maximum normal stress will be positive and this term will be negative. Consider the case where both the maximum and minimum normal stress are negative. Then the maximum normal stress will have a smaller negative value, while the minimum normal stress will have a larger negative value. So we can say algebraically that maximum normal stress will always be greater than the minimum normal stress. Consider now that we are rotating in the anti-clockwise direction. Depending upon the values of tau xy and sigma x and sigma y, we can encounter the maximum normal stress plane first or the minimum normal stress plane first. Let us first consider the case where both tau xy and sigma x minus sigma y is positive. Then tan 2 theta dash is positive. This means 2 theta dash is either in the first quadrant or the third quadrant. Sine 2 theta dash 1 and cos 2 theta dash 1 are both positive. These two give the maximum normal stress. So if we move anti-clockwise, we'll first encounter the maximum normal stress plane, which is given by these two. Now here sine 2 theta dash 2 is negative and cos 2 theta dash 2 is also negative. So the minimum normal stress plane is in the third quadrant. Now consider the case where tau xy is negative but sigma x minus sigma y is still positive. Then overall tan 2 theta dash is negative and will be in the second quadrant or the fourth quadrant. Now if tau xy is negative, then sine 2 theta dash 1 is negative and cos 2 theta dash 1 is positive, which means the plane of maximum principal stress will be in the fourth quadrant. Now sine 2 theta dash 2 is positive and cos 2 theta dash 2 is negative. That means the plane of minimum principal stress is in the second quadrant. So in this case, if we start rotating in the anti-clockwise direction, we'll first meet the plane of minimum principal stress, and then we'll meet the plane of maximum principal stress. So in this case, the plane of minimum principal stress is in the second quadrant, and the plane of maximum principal stress is 180 degrees less, that is in the fourth quadrant. We earlier obtained the expression of tau x dash y dash. We earlier designated the angle at which the maximum and minimum normal stress occur as theta dash. Then we found that theta dash is given by this equation. Two values of theta dash will satisfy this equation, which we designated as theta dash 1 and theta dash 2. We obtained the values of sine 2 theta dash 1 and cos 2 theta dash 1. We substitute these two values in the tau x dash y dash equation. After substitution, we get tau x dash y dash is equal to 0. If we had substituted sine 2 theta dash 2 and cos 2 theta dash 2 in this equation, then again we'll have obtained tau x dash y dash as equal to 0. This means that the shear stress associated with the maximum and minimum normal stress or the principal stress is 0. So here in this diagram, if these are the maximum and minimum normal stresses, then this element will have no shear stress acting. We discussed about this phenomenon physically earlier. Now this behavior has been algebraically proven. Earlier we obtained the direction and magnitude of the principal stresses by using the equation of transformation of normal stress. Here we will obtain the direction and magnitude of maximum and minimum shear stress in a similar way. This is the equation of transformation of shear stress. We find the direction of maximum and minimum by setting this derivative to 0. The angle of maximum and minimum shear stress is denoted as theta double dash. Differentiating this equation with respect to theta and equating it to 0, we get tan 2 theta double dash is equal to minus bracket sigma x minus sigma y divided by 2 tau xy. As earlier, since tan 2 theta double dash is equal to tan bracket infinity plus 2 theta double dash, there are two values of theta double dash which satisfies this equation. We have designated the two angles as theta double dash 1 and theta double dash 2, corresponding to maximum and minimum shear stress. The angles theta double dash 1 and theta double dash 2 are separated by 90 degrees. As earlier from the equation tan 2 theta double dash, we obtain sine 2 theta double dash 1 and cos 2 theta double dash 1. Since cos 180 plus alpha is equal to minus cos alpha, and sine 180 plus alpha is equal to minus sine alpha. We get cos 2 theta double dash 2 is this term with a negative sign, and sine 2 theta double dash 2 as this term with a negative sign. So in this term, in the numerator, we get sigma x minus sigma y. Now we have obtained the directions correspond to maximum and minimum shear stress. We substitute the angles in this expression to get the magnitude of maximum and minimum shear stress. We first substitute sine 2 theta double dash 1 and cos 2 theta double dash 1 in this equation. We then get this term with a positive sign. We then substitute sine 2 theta double dash 2 and cos 2 theta double dash 2 in this equation, and we get this term with a negative sign. So we have tau x dash y dash maximum with the positive sign corresponding to theta double dash 1, and tau x dash y dash minimum with the negative sign corresponding to theta double dash 2. Consider now rotation in the anti-clockwise direction. If we keep on rotating, then depending upon the magnitude of the stresses here, we'll come across the maximum shear stress plane first or the minimum shear stress plane first. Consider the case where minus bracket sigma x minus sigma y is positive and also tau xy is positive. Then tan 2 theta double dash will be positive, and 2 theta double dash will be in this quadrant or this quadrant, that is the first or the third quadrant. Sine 2 theta double dash 1 will be positive, and cos 2 theta double dash 1 will also be positive. Then the plane of maximum shear stress will be in the first quadrant. Cos 2 theta double dash 2 would be negative, and sine 2 theta double dash 2 will also be negative. So the plane of minimum shear stress will be in the third quadrant. Now consider the case where sigma x minus sigma y is positive and tau xy is also positive. Then tan 2 theta double dash will be negative. 2 theta double dash will then be in the second quadrant or the fourth quadrant. Sine 2 theta double dash 1 will be negative, and cos 2 theta double dash 1 will be positive. So the plane of maximum shear stress will be in the fourth quadrant. Cos 2 theta double dash 2 will be negative, and sine 2 theta double dash 2 will be positive. So the plane of minimum shear stress will be in the second quadrant. So in this case, if we rotate anti-clockwise, then we'll first encounter the plane of minimum shear stress. The direction of principal stresses was found using this formula, and the direction of maximum and minimum shear stress was found using this formula. If we multiply tan 2 theta dash and tan 2 theta double dash, we get minus 1. which means the angles 2 theta dash and 2 theta double dash are 90 degrees apart. This indicates that the angle theta dash and theta double dash are 45 degrees apart. Consider that we are in the direction corresponding to the maximum principal stress. If we rotate 45 degrees anti-clockwise, then we'll come to the plane of minimum shear stress. From the plane of minimum shear stress, if we rotate another 45 degrees in the anti-clockwise direction, we'll come to the plane of minimum principal stress. From the plane of minimum principal stress, if we rotate another 45 degrees in the anti-clockwise direction, we'll come to the plane of maximum shear stress. Earlier we found the shear stress associated with the principal stress. We found the shear stress to be zero. Here we'll find the normal stress associated with the maximum and minimum shear stress. Function of the maximum and minimum shear stress was given by the angle theta double dash, where theta double dash could be obtained from this expression. We earlier found that sine 2 theta double dash 1 and cos 2 theta double dash 1 can be given by these expressions. The transformation of sigma x dash with theta was earlier determined to be given by this expression. Considering theta here as theta double dash 1, we substitute the cos and the sine value. Substituting the cos and sine value, we get sigma x dash as equal to sigma x plus sigma y divided by 2. If we had used the expressions for theta double dash 2, then we would have got the same expression for sigma x dash. So the normal stress associated both with the maximum and minimum shear stress is sigma x plus sigma y divided by 2.